talks, I'm going to report on joint work which I've been doing with Martin Bendersky, Fred Cohen, and Sam Gittler. Now, so I'm going to describe some new constructions in toric topology. Most of it is online, but some of the newer stuff is not up yet. Okay, so I'm going to discuss polyhedral products. I'll be very clear about my definitions presently. Now, a polyhedral product, and I know that many of you in the audience are experts, more expert than I am on some things, I'm sure, but I hope you'll bear with me, those of you who are experts, I hope you'll bear with me while I make some elementary definitions. So it's familiar spaces from a different point of view. And the polyhedral product is a functor of two variables, a simplicial complex, and the simplicial complex in my talk always has dimension n-1. So, I want to record these numbers. So, K has dimension equal to n-1, and it has m vertices. It's a beautiful blackboard. So these two numbers, m and n, will not change during my whole talk. They will always be the same numbers. Now, the second ingredient is a family of CW pairs, xi, ai, and it's very important, not so much in this talk, but perhaps in my second talk more so, that there be a base point for these spaces. Right, the base point is very important, and I have one of these pairs of spaces, xi, ai, one for each vertex of the simplicial complex. One of them for each vertex. And with this information, a simplicial complex and such a family, I'm going to associate a topological space, which I'm going to call the polyhedral product. And the topological space will be a subspace. The topological space will be a subspace of the product of the x's. Now, indeed, if the simplicial complex.
You can use this point.
Oh, I don't point. Yeah. So if K equals the simplex which has m-1 m vertices, then the polyhedral product, I hope I've indexed that correctly. Now, XA stands for the whole, is equal to the full product of the x's. So if K is a simplex, it's the full product. If K is got missing faces, it's not the whole simplex, then this topological space will be part of the product, a partial product, if you like. Okay, so now, how do I will define this space as a union, a natural union of subproducts. Strictly speaking, a colimit, and in fact, in much of our work, the fact that it is a colimit of a diagram is very important, critical, but not so much for today's talk. So today's talk, this topological space will be a union of spaces. All of the spaces will be natural subspaces of the product. So there are no gluing maps other than the identity. Okay? Actually, when we first started the reason that our project started is someone asked a very stupid question, namely, if you take products of circles and disks and glue them together with the identity map, can you make a space which has torsion? So Fred, Martin, and I, we all produced proofs that you couldn't. And we were all wrong, all the proofs were wrong. So by taking circles and disks and gluing them together with the identity, not degree 2 or anything like that, you can produce a space which has torsion. We didn't, that came as a surprise to us. But anyway, that was an aside. I distracted myself. And this is the definition. So for each simplex sigma in K, we define a subproduct. Here it is here. Corresponding to sigma in K, we make this product, each which is a natural subspace of this. And if I is a simplex in sigma, we put the factor xi. And if I is not a simplex in sigma, we put ai, and then the polyhedral product is the union of these natural subspaces. Now, these have a long history in homotopy theory, but people were not describing them in this way, a very long history. Now, Fred claims that if you go back to the thesis of Poincaré, you will see this, right? But described as, in special case of this, described in terms of intersections of quadrics. So Fred is certain that this goes back to Poincaré. So this is a very simple construction. I will now give an example. Here is a trivial example. My simplicial complex is just two disjoint points. So it has two simplices, two zero-dimensional simplices and no one simplex. And so in this example, the n equals 1 and the m equals 2. So I must give two spaces in my family, and I choose the 3-disk as x1 and s2 as a1, the 2-disk as x2 and s1 as a2. So then the pieces are corresponding to the first simplex. V1 is in, so I put x factor, and then V2 is not, so I put s factor. In 2, V1 is not in it, so I put a. 2 is in it, I put x. So I get these two spaces, and the union is along the empty simplex, and I get this union that. And the important point is that you get this, the boundary of the product of D3 cross D2. See this? Now as topologists, we would jump to recognize this as S4. But in this context, that is bad, right? Good, bad. So the whole point is we want to look at familiar spaces from this product's point of view. And in fact, those of you familiar with the Hough invariant, the Hough map, the Hough map sees the Hough map from S3 to S2, very famous map in homotopy theory. It sees the 3-disk as the boundary of D2 cross D2. It does not see the 3-disk as the boundary of D4. Okay, so in fact this point of view is very important in that context. So I put this here just to give confidence that we know what we're doing. But I'm really interested in this. This has more information than that. That's the whole point. Yes?
Can you say more about this, the Hough maps? The Hough,
yeah, sure.
this is
Yes, certainly. I'll do that. So to get S3, by the way, I would take K equals 2 points, and I would take XA to be D2S1, D2S1. So I would get D2 cross S1, union along S1 cross S1 with S1 cross D2, and this is the boundary of D2 cross D2, which is the 3-sphere. But more than that, let's see how that appears. Let's see how that 3-sphere appears. So the 3-sphere, that is best seen by looking at the 3-sphere as S1 join S1. So here's a picture. This is not a boundary component. It is just a circle embedded in S3. So here we are. and I take generic fiber a T2. So this is S1 here, this is S1 here. In fact, I start with T2 cross the unit interval. A cylinder, and I identify one coordinate circle as a group here and the other coordinate circle as a group here. So that leaves me S3, which looks like S1 join S1. Now let us find in there, let us find these D2 cross S1 and S1 cross D2, right? Let us see them. Well, here is a D2. I take one circle going around there, and I follow those circles to a point on there. So this is D2. So this side of the 3-sphere is D2 cross S1. And the other D2, I take these meridian circles, and this is D2 as well. So I have D2 cross S1 union S1 cross D2 along S1 cross S1. Now the circle, I take the diagonal circle inside S1 cross S1. This diagonal circle acts freely, preserving the vertical fiber. So in fact, it preserves the structure as a polyhedral product. And what it does is identifies these disks. The circle acts on a disk, and it gives me an interval as the orbit space. And then, because it acts freely, this circle gets identified to a point. So all of these disks, all of these red disks get identified to the same disk. And so what I get, so I get this rotated this way. And then the other way, I get, it depends how you want to point of it, but it might look like this. This is one of those D2s. So it's D2 here. Here is D2 here. And the circle cross the circle modulo this diagonal action is S1. So I have D2 union D2 along S1. And this is CP1, the 2-sphere topologically. And the Hough map is this identification. So it is S3, this S3, modulo that diagonal circle action. So that is the Hough map. Okay? So that took me a little off course there. Okay, so here is an example of a polyhedral product. Now let me just set the definitions straight, because there's a lot of confusion in this subject about the meaning, the words that we should use, and I think Taras and I agreed finally on what we should use. So if XA is the same for every I, we call it a moment angle complex. This is terminology which you've probably seen. If XA is equal to the collection, say, D2J1, S2J1 minus 1, etc., down to D2JM, S2JM minus 1, then it's called a generalized moment angle complex. Or, as Fred likes to say, Big Mac, right? Big Mac, Little Mac, Big Mac. And D1S0 is the real moment angle manifold, and that will feature prominently in my talk Wednesday at 2. And then everything else is a polyhedral product. Now, why this? I want to tell you some of the history of this word, polyhedral product. This phrase was constructed especially for us by the same person who invented the word orbifold, right? So the person who invented orbifold invented polyhedral product, and that person is Bill Browder, the famous homotopy theorist Bill Browder. So this is official name. So that's our terminology. Now, you know, these things show up in a variety of subjects. This is the tip of the iceberg. The D2S1 case is related to toric varieties, singular and non-singular. C star is complements of coordinate subspace arrangements, but not just coordinate arrangements. Not just coordinate arrangements, right? Not just coordinate. This case here and this case here, they're related to combinatorics of K, the Stanley-Reisner ring. This one here is related to the intersection of quadrics and small covers, those of you familiar with. Also in robotics, engineering, group theory, monomial ideal rings, we just use these things to prove a theorem that you can realize any monomial ideal ring with a topological space. And in fact, Fred has been working with some engineers, and there is a movie of a robot, like a spider, climbing over impossible obstacles using moment angle complex. Well, not quite moment angle complex, it's a polyhedral product. S1 comma S1 plus the upper hemisphere of the circle, because you've got to make sure so many feet are on the ground. So using this, moment angle complexes make robots move. And as you can see, this is just the tip of the iceberg. You can see you have your fair share of experts in Korea. So this is, a lot of people work on this stuff. That's about half the list. Okay, so now I'm going to begin my talk, at last. I'm going to begin my talk, and let me just say what I'm going to do. I'm going to begin by describing a construction on simplicial complexes, and I hope to have the time to tell you what is happening on the level of the Davis-Januszkiewicz construction with which you might be familiar. So I'm going to start with a simplicial complex where I have the numbers m and n, and I'm going to be given a sequence of positive integers, j1, j2, up to jm. M is the number of vertices. And from that information, I'm going to make a new simplicial complex. Much bigger, much larger than K. Much larger than K. Now, there is an explicit construction for making this simplicial complex, but I won't be describing the explicit construction today, but I'm going to describe the simplicial complex in the following way. One way to describe a simplicial complex is to start with a simplex with m vertices and then remove simplices from it until you reach your simplicial complex. Every simplicial complex embeds in a simplex. So all I need to do is only thing I need to do is to specify the simplices which are missing from the simplex. And that will tell me what the simplicial complex is. So here is my definition. Now I know that this is very complicated here, but I'm going to follow the rule which I learned of, which was the rule of Gelfand, who said, show me a trivial example and I will work out the complicated one for myself. So that's what I'm going to do. But I will go through this. So K has m vertices and you give me this string of natural numbers. Now the new vertices of K of J, see the vertices were V1, V2 up to Vm. Well, K of J will multiply V1 J1 times, V2 J2 times, and so on. So each vertex is increased. The number of vertices is increased in corresponding order with the ji's. And the rule for defining the simplicial complex is I made a mistake. No, it's black here, but it's blue here. That's it. I thought I'd made a mistake. I thought I'd put color blue throughout my text file. So here is the rule. Here is a missing face of K. Missing face of K, right? So it's got VI1 here, VI1. Now that VI1 must be repeated JI1 times. And where VI2 appears, it is repeated JI2 times. So the missing faces are going to be in one-to-one correspondence, right? That's the point here. The missing faces and all missing faces will be given by this rule. So let's look at a simple example. Oh, what? Oh, sorry. Orientation problem. Here is a trivial example. So I start with K, two vertices, V1 and V2, and I'm going to take J to be 2, 1. So here, K is just two vertices, and J is has to be length M, so M equals 2, N equals 1. So J has to have two entries, and it's going to be 2, 1, right? So here, the minimal missing face is V1, V2 is missing. See? V1, V2 is missing. Now, because it's 2, 1, then the new vertices, so here is K of J, so the vertices of K of J will be V1 is doubled, so it'll be V11, V12, but 2 remains single, but I give it a new name, V21. So K had two vertices, K of J has 3 vertices. The new M equals 3. And there is one missing face, V1, so there's only to be one missing face here, and V1 is converted to V11, V12, and then V2. So this has to be the only missing face, right? So it's 3 vertices, and so that gives me, this is the only missing face, so this J construction, it converts 2 points to the boundary of a 2-simplex. Very simple construction, right? Trivial construction. But I hasten to add, there is an explicit construction. So this is explicit, but I'm not taking up my time today to say what it is. I will have to say so in perhaps another talk. So this is explicit construction. And it's called the simplicial wedge construction. We thought we invented it, right? Okay, so let's see, what is the use of such a construction in the context of polyhedral products, right? Well, very shocking.
Can I ask a question?
Certainly, yeah.
Did this process preserve the pureness of the simplicial complex?
Yes, it does. I have to check that, but
yeah.
The answer is yes. Okay, now I have to make a convention now. So my original, I started with M pairs, XIAI, M. Now, if I want to make this polyhedral product, this is impossible. This is impossible here because K of J has many more vertices than M, right? And XA, it only has M pairs, right? So this is an impossible construction, right? But what I do, my convention is that I repeat JI times each XIAI. I repeat, it's understood, right? So it's an abuse of notation, but strictly speaking, it is impossible because there are too many vertices here, but this is abusing notation convention. Okay, just repetition. Okay. So let's look, I think, at an example here. Oh, no, I haven't said what I want to say yet. Now, I want to now investigate what is the effect of this K of J on polyhedral products, right? And it's rather extraordinary, surprising. And what I'm describing here is just the tip of the iceberg, right? This is the simplest case. K of J, for those of you who are familiar, what's going on here is these numbers, they index simplices. But that's invisible in what I'm doing. They index simplices, so I can move more generally than simplices. But there is a product on CW pairs. You take the CW pair x comma a, Cartesian product with y comma b, and it gives you a new CW pair, x comma y, x cross b union a cross y, and the union is along A cross B. Okay? So that is the Cartesian product on CW pairs. So if you give me a string of J's, I can make a new family of pairs YB. And YKBK will be XKAK multiplied by itself JK times in this rule. So I'm exponentiating CW pairs, right? So here's a theorem. These two polyhedral products, where this is the small simplicial complex, this is the big simplicial complex. So in my talk, you want to think of this side as better than that side. This J construction, it carries exponentiation of polyhedral products, right? This is a bad word, equivalent. They are equal. No diffeomorphism, no homeomorphism, equal. This equals this as subspaces of this very big Cartesian product. So that is this particular application. That's not the only property of this K of J, but it's the property which is important for me today. And so if I exponentiate the pairs, now the important point about this is that the combinatorics of K is less than the combinatorics of K of J. That's the key point. Yes?
Do you have a characterization of the K of J? For example, if I give you a simplicial complex?
Okay, I can give you a necessary condition. So for example, it has to have a group of symmetries, right? So if J is 2 and everything else is 1, there has to be a Z2 action which fixes certain things. So it has symmetry. Not every K is a K of J. But we thought we could completely classify them. But I can give you necessary but not sufficient conditions. So, but I will tell you a rather shocking thing that follows from this, which we did not notice. Somebody told us that our theorem says this, and we did not notice, but it turns out to be quite important. And we'll follow in some remarks I want to make. So that's the point. This K of J, it carries exponentiation of pairs. All right? Now, there are a lot of applications of that. Here is an example. I start with 2 vertices. I take J equals 2, 1, so I am going from 2 disjoint points to the boundary of a 2 simplex, right? And I take XA to be D2S1. In other words, every XA is D2S1, the 2 disk and the circle. So Y1, it's DX1A1 raised to the J1, and the J1 is 2, so you square it. And when you square this pair, you get this. You get the 4 disk and its boundary. But I don't want to call it the 4 disk. It's very important that it's D2 cross D2. And then the next one, the J is 1, so I just raise it to the first power. And so what do I get here? I get that this is the boundary of this 6 disk, which is the 5 sphere. Now the important point here, now it's not a secret that we can construct the 5-sphere as a polyhedral product. The important point is that I've constructed the 5-sphere from 2 points, right, from 2 points. So, you know, I'm going to be able to construct every complex projective space from a one-dimensional fan. Every complex projective space with a toric variety from a one-dimensional fan as a toric variety. Right? So this is a trivial example, but it does get better. Okay, now there are 2 remarks, and the first remark is very shocking. This was what was pointed out to us. Every complex moment angle complex is a real moment angle complex. Every D2S1 is a real one on the nose, right? Now we are not going backwards. Now this is pretty surprising because when you look at the ring theory of the cohomology of this, it can have exotic products. There can be exotic products. And I'll say on Wednesday what I mean by exotic. But this is saying this can have no exotic products. So what this is saying is that for simplicial complexes, which are K of J's, there can be no exotic products. And in fact, as a conjecture, for those of you who are experts, here's a comment for those of you who are experts. If I look at ZK D1S0, ZK D1S0, now we all know that the cohomology of that is Tor as a group, not as a ring. It's the Z2 Tor, same as the complex case, but only as a group. So I conjecture that for K equals K of J, it is equal to the Z2 Tor as a ring, right? That's just conjecture. Now, so to get from here to here, J has to be all 2's. All 2's, right? And then this side is the same as that side. And so these results long ago when we first thought of them, even though there was a problem with attribution, this has been applied to this toral rank conjecture of Buchstabe and also to the homotopy type of products associated to shifted complexes. And there are other applications as well. So now I just pointed out here that for years Santiago Lopez de Medrano was working on intersections of quadrics, complex and real quadrics. And he was speaking to my colleague Sam Gittler, and they realized that these were these moment angle complexes. And in fact, the connection between moment angle complexes in the intersection of certain quadrics is implicit in later work of Buchstabe and Panov, but that came much after Santiago Lopez de Medrano, although it is implicit in their work, and then in a recent paper they make it explicit. Now, this J of construction in a certain instant when these are quadrics, and they're not always quadrics, only some real moment angle manifolds arise as quadrics, only some. And they're connected sums of products of spheres. Well, there, if you double the variables and duplicate the coefficients in the quadrics, you get something like what we're doing here for 2, 2, 2, 2, 2. So this is a phenomenon that's been seen, but although Santiago didn't know what that these were related to polyhedral products or anything like that. Okay, so my concern is to relate this information to the topological study of toric varieties and toric manifolds. Now, I have to say what a toric manifold is. Well, here is the model for the toric manifold. If you take the complex numbers, there is a standard action of the circle on the complex numbers, and this is the orbit space. And it turns out that this copy of R+, that's a combinatorial object. This is a polytope. So this is the connection between toric geometry and combinatorics. Right here. That's all there is. And in fact, if I take Cartesian product the same thing happens. In Cartesian product, I get the action of an n torus, but instead of getting R plus, I get the positive octant. So this is quotient by the n torus. So now I'm in a position to tell you what I mean by a toric manifold. Every smooth, well, every non-singular toric variety, projective toric variety, will be a toric manifold in my sense. Okay. Now, let me just say what I mean by it. So, now this is not a construction, it's just a definition. So, M2n's got to be an even dimensional manifold, is a toric manifold. This is in the sense of Davis and Januszkiewicz. That is what they called them, by the way. As far as I know, there is no other name for these objects, right? Some people use other names, very ugly terminology. If you want to write ugly English, be my guest, right? Okay, so it's a toric manifold. So I have to have a covering by Cn patches. So it has to have a covering by Cn patches. Now also, there has to be a global action of the n torus. So I have a covering by Cn patches. I have a global action of the n torus such that when I restrict this to this, I get this standard action, right? So such that the n torus restricted to a Cn patch is the standard action. And I'm not finished yet. So each one of these will give me one of these, right? And the final requirement is those Rn pluses, they must fit together to give me a polytope. A simple polytope. The quotient must all fit together to give a simple polytope, which in the neighborhood of each vertex looks like Rn plus. So these have to all, this becomes a vertex of the polytope. So in the neighborhood of each vertex, the polytope, which is the quotient of this action, it must look like this in the neighborhood of a vertex. So here is M2n. It has a global action, and I get this polytope. And I'll draw a picture. Next slide, I think there's a picture of CP2 as a toric manifold. Here is CP2. So this picture tells us that CP2 has a covering by three C2 charts, given by just choosing your coordinate to be 0 in different spots. There is a global action of the 2 torus on CP2, and on each patch it gives me Rn plus. Here is Rn plus, R2 plus, R2 plus, and they fit together to give me a 2 simplex. And it is this property which makes CP2 a toric manifold. Okay. Now this does not tell you how to construct a toric manifold, right? But we topologists, thanks to Davis Januszkiewicz, and this is the construction with which I'm most concerned today, but I'm not going to get to the main point of my talk. But I want to change this construction, you see. So to the topological approach to non-singular toric varieties, you have to have 2 ingredients, a simple polytope of dimension n and a set of facets, m facets, and n and m are the same in my whole talk. And we have to have a map from the set of facets, m of them, into the n lattice, which you can interpret as assigning an integer vector to each facet of the simple polytope, although there's no special reason to do that. In fact, it's better. It can be considered as a matrix. So this extra information is a matrix. This is, for those of you who are familiar, this is the information that takes into account the rays of the fan, and I will say more about that in my talk about singular cases, weighted projective spaces, on Wednesday. So I consider this as a matrix. Now I put a condition on the matrix. So I have a matrix, and my matrix has n rows and m columns. So here is my matrix lambda. So it has n rows and m columns. Now the columns, they are indexed by the facets of the polytope. Each facet indexes, and the requirement, now at each vertex of the polytope, I get n facets meet. Now, so every vertex determines an n by n minor of this matrix. Every vertex, and I insist that to be plus or minus 1. On Wednesday afternoon I won't, but in this case here I insist that that be plus or minus 1, and this is the regularity condition which will ensure that the construction does give me a manifold. Now, if I look at the Lie algebra, I can regard the M torus as a quotient of the Euclideans, of the real numbers, and so there the kernel of lambda determines a subtorus. So all that's important to me, instead of this matrix, all that's important to me is a choice of subtorus in the M torus. That's all that's important to me, and here's one way to construct it. Okay. Now, so it's an M. So Davis and Januszkiewicz make two constructions. There are two constructions. One involves the M torus and the polytope, and the other one of the toric manifold, which I've not said how the construction goes. It is made from the quotient of the N torus type Pn. So what do these constructions do? These are very different constructions. These are very, very different construction, and in fact the gist of our work is to convert the bottom construction into the top one, right? That's what we're going to do. Now what does it mean to do these constructions? Well, when I look at the N torus or the M torus, let's look at the M torus, I want to think of this Cartesian product as, here's my polytope, and then above each point I have a torus, above each point, like this. So this is how I regard the product. And these equivalence relations, they are going to make identifications on these tori, right? They're not going to join any of the tori together. They're just going to be quotients of these tori. That's what these constructions do, right? Now the important point is this first construction does not involve the map lambda, but the bottom construction does involve the map lambda, and that's a big obstruction. In fact, we do not need to make this construction involving the map lambda in the equivalence relation, right? We don't need to do that. And that will allow for generalization, which will fit very well with my K of J construction, right? So these are two constructions of Davis and Januszkiewicz and others. Now, in order to say more about the constructions, I need a duality between the polytope and the and a simplicial complex, which can be expressed in various ways using the polar polytope. But just as a combinatorial description, this is my polytope, this is my simplicial complex. The facets here correspond to vertices, and intersections of facets correspond to simplices. That's all. Okay, now I can describe the cohomology of one of these spaces, and the cohomology ring, it's people look at this answer for this Danilov-Yurkovich, Davis-Januszkiewicz, both DJ by the way, doesn't matter which one you say, Davis-Januszkiewicz or Danilov-Yurkovich. This looks like a very simple answer, but it's not. It's an impossible answer, right? So some people look at this answer for the cohomology and they think, oh, that's a very nice answer, right? That's a very nice answer, but it's not. Very difficult answer, actually. And so it's a quotient of it's a nice presentation. It's a quotient of a polynomial ring by two ideals. One ideal comes from the matrix lambda, the rows of the matrix lambda. That's Lm, and the other ideal is this ideal of relations corresponding to the non-faces in the simplicial complex K, which is dual to the polytope. Okay, so that's a description of the cohomology. Very good. Okay. That's why I needed to. Now, how do these moment angle complexes get involved in this subject? Well, I'm going to describe the first of these constructions. Here is the polytope, and we are looking in the neighborhood of the vertex, and the constructions are local in this sense. I can just look at the neighborhood of the vertex. So instead of looking at the M torus cross the whole polytope, I'm just going to look at the M torus cross the neighborhood of a vertex, which looks like that. And then what I do is everything here is indexed by the facets of the polytope. So this ordering, it's not correct. If you give me a vertex, there is an ordering where these pieces are distributed throughout the Cartesian product in their correct order, right? And so I take the n copies which correspond to that vertex, the facets that correspond to that vertex, and I leave the other ones, the other circles in here, I leave them alone. So I make that decomposition. Fair enough, make that decomposition. And then what is the equivalence relation do? Well, it takes each cylinder, remember it was a Cartesian product of cylinders, it takes each cylinder, identifies one of the coordinate circles to a point to make a two-disk. These are the circles which are left over. Everything else becomes two disks. So when locally, it consists of the equivalence relation locally, it creates disks and circles, right? Disks and circles. And now I assemble this big product. I assemble those together according to the polytope, the vertices of the polytope, and that gives me a polyhedral product, right? That's how I make my polyhedral product. So, as I said here, the lambda determines a subtorus. So what I did just now for you, I showed you why this was this, right? That's this line here, that's the identification. And now, the M torus, it acts on the M-fold product of two disks. So in particular, acts on D2 to the M. So in particular, Tm minus n, which is the kernel of lambda, which is contained in the M torus, this acts on D2 to the M, and hence, because subspace of this, invariant subspace, hence on the polyhedral product. So it acts on this. So now I can take the quotient by this action. And so this equivalence relation It is the equivalence relation which I put here to make this diagram commute. Now, because on this side we have used lambda, lambda must appear here. Okay? Okay, I'm clearly not going to get to the beginning of the main part of my talk. Well, here's a picture for you. So remember, here is what I start with when I make the toric manifold here. Here's what I start with. And now the equivalence relation makes identifications, and you can see here, this is the 2 simplex. Circles have been identified in the torus here. And what I'm left with S2 here, which is a copy of CP1, S2 here, which is a copy of CP1, CP1, and then in the interior, there's no identification. So in the interior here, there's no identification. The identification occurs along facets and intersections of facets. And this is how you make CP2. I've not told you what the lambda is. I've just told you what the answer is. Here it is in this Davis-Januszkiewicz terminology. Now, I've run out of time, so I'm going to jump to the end of my talk. Okay? This is about a third of the way through it. Well, here is the point of my talk. Okay? To make CP2, here is CP2. To make CP2, I have used the combinatorics of the 2 simplex, right? The combinatorics of the 2 simplex. But what I discover is that I don't need to do that. We arrange the Davis-Januszkiewicz construction so I can make this picture. I can make this picture with a 1 simplex instead of a 2 simplex. Not only can I make it with a 1 simplex, but I can describe its cohomology with simpler combinatorics, right? Because the 1 simplex is smaller than the 2 simplex. And the way that I do this is that instead of using I use bigger disks, right? So here I'm going to use, bigger disks, 4 disks, say, right? So I use bigger disks, and by the theorem which I told you, this is going to be Z of K of J of D2S1. And the interesting thing, which we made K of J to satisfy this exponential property, and when I approached Carl Lee, a combinatorial theorist, I asked him, have you seen this construction, expecting him to say, why do you want to make such a stupid construction? He said to me, that's a very important construction. It's called the simplicial wedge construction.
Are you saying that D1 is 0?
D2S1.
K,
No, this is what I've written here. This is an ordinary toric manifold, right? It turns out that if I put big disks here, this is equal to this by the exponentiation theorem. Now, not only that, but if this is dual to a simple polytope, this is. That's what Carl Lee and also Taras Panov, once I told Taras about it, he told us that that's dual to a simple polytope. And Carl Lee, and in fact it's an old construction that goes back to Belira and Rose, and it is called the simplicial wedge construction. And so this allows us to make complicated toric varieties with much less combinatorial information. Now, I'm going to go to the end of my talk to show you another picture of CP2, right? But unfortunately, I have to go there through my slides.
So you're already out of time, I have a question. But you have a big restriction on the complexes that can appear. You cannot build like this all...
No, not all. What I'm saying is, if you start with a single toric variety or toric manifold, just one, From that one, I can construct infinitely many.
Okay.
So for every one you give me, I will construct infinitely many, and the cohomology of them will be described in terms of the original one and the original fan, right? Not the... Okay, so here, this is what the new lambda looks like. M of J is the new toric manifold. Here is a simpler description. So I give there an example of the two descriptions. Now, this part I didn't deal with, but this construction corresponds to replacing the circles in the Davis-Januszkiewicz construction. See, the Davis-Januszkiewicz construction is tilde prime, but instead I replace this Tm by Tm minus n cross Pn, and this has no lambda in it. Lambda is here, and it corresponds to doing the Davis-Januszkiewicz construction with odd spheres, bigger than circles. But anyway, let me jump right to the end of my talk. And here, I'll go one more slide. Okay, this was the original description of CP2, which I put on the board. This description is the new description where the construction is indexed by an interval instead of a two-simplex. And this is just the first trivial example. And also this is related, we show that this construction where we use bigger spheres corresponds to this construction over here. And that is the gist of these new constructions that I was wanting to talk about.
So this identification, what's the equivalence of the torus actually?
Yes, these are, in fact, these two things here, this and this, they are equivariantly diffeomorphic with respect to the Tm action. And the kernel of lambda, I make a much bigger lambda, but it turns out the kernel is exactly the same.
Yeah, but then there's supposed to be bigger torus acting on the Z or KJ.
That's correct, but the M torus acts on this by repetition.
Yeah. So that identification, I mean, you can't talk about it for the bigger torus.
No, no, but that's the point is here that there is a lambda on this, right, that sits inside the bigger torus, right? The lambda is different, right? And that the kernel of lambda is the same size, but it's acting diagonally here, right? It's acting diagonally, but we need this identification because we know when we take this object and we mod out by the kernel of lambda, I skipped through, I showed you a big matrix, that was the new lambda, then that gives me an ordinary toric manifold. So I know the quotient of this is an ordinary toric manifold. So I need that to know that the cohomology is concentrated in even degree. You see, that's a big problem in the subject now for a lot of reasons.
So, but you're saying that the kernel to get the original toric manifold,
yes,
which is the quotient of the
exactly, yes,
kernel sits inside of
in the same way.
Sits inside of Tm, which acts in both.
That's correct. Tm acts on both, sits inside it in the same way. Okay.
The bottom one has originally much higher.
That's correct. It sits.
He's only considering some diagonal.
That's right. It's
To the nth power.
exactly. With respect to those increased diagonal actions, they're equivariantly diffeomorphic. And so that allows me, you see, if I wanted to describe the cohomology of CP2 in the bottom here, I would have to take three generators. So it would be, and then the linear ideal, there would be a linear ideal which said that V1 is V2 is V3, and the monomial ideal relation would be V1, V2, V3. So this is CP2 described, the cohomology of CP2 described in the traditional way. Now, if I start with the one simplex and I let lambda equal 2, 1, I let j equal 2, 1, right? The cohomology description I get only has 2 generators. This is a trivial case, I admit. It has 2 generators. The linear relation is that they're equal, but instead of this, I get V1 squared V2 is the relation. So the monomials are no longer square free.
So basically, like if you're on the top ZK, and in this equivalence of 2 spaces somehow.
This one here, this one.
Yeah, so that one, you just replace D2 and S1 by those higher.
That's correct, but I don't know as much about this. But
what about the equivariant cohomology of that space with that T?
Okay, well the equivariant cohomology of this will be the equivariant cohomology of that. They will both be the Borel construction on the toric manifold.
So basically, you're back to the known ones.
The point of this is these are the known ones.
Yeah.
These are the unknown.
Yeah.
See, the point is that I never want to go here. I just want to go here for theoretical reasons, because I need to know that I have a toric manifold, right? But I never go here. In fact, the whole theory is developed for this. So if I could just go back to a slide, I'll show you how that theory is. The whole theory changes, but in a sort of controlled way. If I just go back, this is a new Davis-Januszkiewicz construction, but I'm not really spending a lot of time here. Okay, so there is a canonical fibration in toric topology, right? But here, this is the associated fibration. So instead, what would the Stanley-Reisner ring be? The Stanley-Reisner ring would be CP infinity comma a point here. But that doesn't happen. Instead, I have here this more complicated polyhedral product. Now, the cohomology of this is the generalized Davis-Januszkiewicz space. Now, the cohomology of this is like a Stanley-Reisner ring, but the ideals are no longer square free. Okay?
But you can describe it combinatorially, purely combinatorially.
Yes, exactly. From K. Yeah. See, what I'm describing toric varieties which have this combinatorics, but I'm describing them in terms of the combinatorics of the original toric variety or toric manifold that I use to describe, that I start with, yes. So from one, I make a family. And they have very interesting I think Su Young came up with the following example when he was visiting me. He gave an example of 2 toric manifolds which were diffeomorphic, right? Diffeomorphic, not equivariantly, but diffeomorphic. And he had a J, I think they were Hertzebruch surfaces. He chose a J, he did the J construction to both, and the 2 resulting ones did not have the same cohomology. So not only were they not diffeomorphic, they didn't have the same cohomology. And in fact, in a paper we wrote about the KO ring structure of toric manifolds and the KO theory of a product of projector spaces, which was unknown, we show that you can choose J's to behave so that the toric manifold behaves well with respect to an important subalgebra of the Steenrod algebra, square one. So you can start with a toric manifold. It may or may not have square 2A cyclic homology, but you can choose J to ensure that it does have a cyclic homology. Right? So, but so that's generally the gist of it, right? I mean, excuse me. The first examples are constructing all projective spaces from CP1. So you start with CP1 and a one-dimensional fan, and just using, when you make the toric variety, of course, you're compactifying a torus, right? So the fan is a rule for compactifying a complex torus. Now, how does it do that? Well, the rays of the, the cones of the fan give us partial compactifications of the torus. And then the lattice vectors, they give us the rational functions which we're going to use to glue together the affine pieces. Well, what this approach is saying is you start with bigger affine pieces. Right? And you use minimal gluing information on those bigger affine pieces to get projective spaces, for example. So you can construct, if I just take CP1 and I take J equals K comma 1, I can construct every projective space. And it will have cohomology described like this. It will have two generators, and that if I just use K1, it will say V1 to the K, V2 is 0. In that case. But this is not really, of course I didn't have time to, this funny, I gave this talk in an hour not so long ago, a similar talk, and yet I didn't really get far today. But the important point that I was wanting to make in this talk is the generalization of the Davis-Januszkiewicz construction. Because this generalizes the Davis-Januszkiewicz construction to using odd spheres and still getting toric manifolds. Well, you can go beyond that. Instead of an odd sphere is a moment angle manifold, right? So you can put any moment angle manifolds in there. All you need is spaces on which S1 acts freely. Okay? So using that you can make far more general object, but the beauty of it is that no matter, if I use moment angle complexes instead of odd spheres, well, my answer is going to be in terms of the cohomology of those and the cohomology of my original combinatorial object, right? So that's not been written up yet. We hope to get to that some point. It's not anytime soon, I'm afraid. That is the gist of it, and recognizing that these spaces which we make from the point of view of moment angle manifolds can be realized by the Davis-Januszkiewicz identification. Once you modify that construction, you have to modify that construction to get this, right?
Does this help to construct more than toric manifold?
Yeah, well, of course, you can do this with singular varieties as well. If you
No, I'm curious about torus manifold.
you could do torus manifolds, although we have not. In fact, I want to tell you something very interesting about torus manifolds. If you're, I've had this discussion with Makia and Taras, but I can't get them to think the way I do. But before I answer your question about torus manifolds, right? In my talk on Wednesday, I will talk about weighted projective spaces whose equivariant cohomology is given by piecewise polynomials, which in a special case is Stanley-Reisner ring. Now there, if you apply the J construction, you get bigger weighted projective spaces. But the important thing is that the cohomology, the piecewise polynomials that you have to look at on the big fan, they're all in terms of the original fan. So for the point of view of equivariant cohomology, that's really... But if you'd like to talk to me afterwards, I will tell you a very interesting fact about torus manifolds that I think, you know, that you can get from a generalized moment angle complex just by taking every factor to be D2S1 and then the last factor to be D1S0, and that torus acts trivially on that. Now you don't get torus manifolds on the nose, but you get things which are retracts of them. So for example, if I did this and I took I think if I took this and I forget which simplex I take, I get as a quotient space a hexagon. Now the hexagon has a standard cubical structure, right? So in the neighborhood of each vertex, you would do this. This is its standard cubical structure. But instead, what you get is this. I have to think about how to do the... You repeat that down here. So, and that gives you a quotient which is S6 sorry, this is a torus acting on S6, and its quotient has this cubical structure. Notice where the vertices are, right? So this gives you some very interesting things. You know? You can do the J construction to that. Do anything that you can express like that, you can do the construction to. So the whole theory gets replaced by this once you analyze. This led to some other work where it's amazing. You can realize every monomial ideal ring with a topological space. This was first proved by Alvise Trevisan, but we didn't know about his work. There's a very trivial proof of why you can realize every monomial ideal ring with a topological space using some regular sequence of Freiberg. But the interesting thing is that many of them can be realized by spaces that look like this, by putting some other projective space here, putting them with points. You can realize a lot of monomial ideal rings with this stuff. But basically, this is how the theory changes when you do this. You know. It would be very interesting, if anybody is interested in this problem, here is a problem that I consider really important. And that is, take a fan, look at it, a very nice fan, and be able to tell whether the cohomology is concentrated in even degree or not. That's a problem that would lead to a lot of consequences. For example, perhaps I'll talk about this on Wednesday, although I'm getting pessimistic about what I can cover. It's in the realm of singular toric varieties. This is an occasion where you can measure precisely the difference in cohomology between an honest quotient and the Borel quotient. With absolute precision, you can see before your eyes the increase in complexity as you go from an ordinary quotient to a Borel quotient, to a homotopy quotient.
It gets more complicated?
Absolutely. So you're looking at gadgets like this. Sorry. This action is not free here. So there's a homotopy quotient. So some torus is acting with finite isotropy groups on that. And then there's an honest quotient. Now, these are two things we study in homotopy theory, this and this. And the cohomology of this, you can measure exactly how much more complicated it is than that. It's got enormous divisibility arises, whereas this one, in the cases that when things are concentrated in even degree, you can see exactly how much the complexity increases going from here to here. This is the much more complicated gadget. Yeah. Yeah. Much more complicated. Yeah, you can see the divisibility appearing before your eyes. Mm. Yes.
Okay. Do you have any questions? Maybe we can stop today. For today. Yeah, for today. And okay, thank you very much.
Thank you very much.